There was a kid named Carl Goss, and once he was in school when the teacher gave him the task to add all the numbers from 1 to 100, thinking it would take Goss a long time. In a few seconds, Goss gave the correct answer, 5,050. Goss thought that if he paired the numbers 1 and 100, 2 and 99, 3 and 98, and so on, each pair would have a sum of 101, and there are 50 pairs, so the total sum is 5,050. This is what is called an arithmetic series. The list of numbers that Gauss added, 1, 2, 3, and so on, is called a sequence. When you add up the numbers to get a total, 1 plus 2 plus 3, and so on, the answer is a series. In Gauss' case, where each number is separated by a certain amount from the previous one, the series and the sequence are called arithmetic. So what Gauss solved was an arithmetic series. Let's have an exercise. Which of the following are arithmetic sequences? Let's look at A. Well, each term is separated by 3 from the previous term, so it's an arithmetic sequence. For B, the difference from the first and second terms is 2, the difference from the second and third is 3, and then 4 and 5. It's not a fixed difference, so it isn't arithmetic. For C, the difference from each term to the one before it is 7, all the time, so it's an arithmetic sequence. An arithmetic sequence is defined by the first term, which you call A sub 1, and the difference between the terms is called D. So the sequence is A sub 1 plus D, A sub 1 plus 2D, A sub 1 plus 3D, and so on. The nth term of the sequence, which we call A sub n, is A sub 1 plus quantity n minus 1 times D, since it is n minus 1 d's away from the first term. So the nth term of A, for example, would be A sub n equals 10 plus n minus 1 times 3, or we can rewrite that as A sub n equals 7 plus 3n. Here's an exercise. Would be the nth term of C? The sum of the first n terms is thus A sub 1 plus A sub 1 plus D plus A sub 1 plus 2D, and so on, the last term being A sub 1 plus quantity n minus 1 times D. We can find the sum using a simple method. Let's call the series S and write it down, and write it backwards underneath. We add the pairs vertically, and we get 2S equals 2A sub 1 plus n minus 1 times D plus 2A sub 1 plus n minus 1 times D, and so on, plus 2A sub 1 n minus 1 times D, where the sum has n identical terms. So 2S equals n times 2, A sub 1 plus n minus 1 times D, or S equals n over 2 times 2A sub 1 plus n minus 1 times D. You might want to remember this formula, but even more important to remember is where this formula came from. Let's have an example. A child's mother gives her 10 cents one day. Each day afterwards, her mother gives her 3 more cents than the previous. After 20 days, how much does she have? We have A sub 1 equals 10, we have D equals 3, we have N equals 20, so the sum is 770. Let's try another one, finding A plus 5 plus 2 plus so on until negative 10. Well, we have A sub 1 equals 8, we have D equals negative 3, we still have to find N. We have the last term, and using the formula A sub N equals A sub 1 plus N minus 1 times D, we can solve for N, so N equals 7. Then we can work out the sum using the formula, which is negative 7. Here's an exercise. Find the sum of the first 100 terms of negative 1 plus negative 99 plus negative 97, and so on. Here's another exercise. Find the sum of the first k integers 1 plus 2, and so on up to k. Let's try a more difficult problem from the AHSME 1952. If the sum of the first 10 terms of an arithmetic progression is 4 times the sum of the first 5 terms, find the ratio of the first term to the common difference. Just remember the formula, it has all the info we need. We know the sum of the first 5 and the first 10 terms are this and this from the formula. So we set the second sum as 4 times the first, and simplifying we get the linear equation 10 times 2a plus 4d equals 5 times 2a plus 9d. Expanding and pulling the variables to different sides, we then have 20a equals 10d, so a over d equals 1/2. Once there was a wise woman that solved the king's problem, and the king said she could have anything she wanted. So the woman asked the king for a chessboard with 1 grain of rice on the first square, 2 on the second, 4 on the third, 8, 16, and so on up to the 64th square. This is what is called a geometric series. A geometric series is just like an arithmetic series, except instead of having a common difference, there is a constant ratio, r. In this woman's case, the first term would be 1 and the common ratio would be 2. Since each term is r times the previous one, a geometric series is a sub 1 times r, a sub 1 times r squared, and so on. The nth term is a sub 1 times r raised to n minus 1. So, for example, the nth term in the woman's case would be a sub n equals 1 times 2 raised to n minus 1, or a sub n equals 2 raised to n minus 1. We can sum the series with a method like we did for the arithmetic series. So, if we take s, and we take s times r, and then we subtract the second row from the first, all the terms in the sum but 2 will cancel. We are left with s minus sr equals a sub 1 minus a sub 1 raised times r raised to n. As long as r is not equal to 1, s equals a sub 1 quantity 1 minus r raised to n all over 1 minus r. Make sure you understand how the sum is found. Let's have an example. Find the sum 2 minus 2 thirds plus 2 ninths minus 2 over 27 plus 2 over 81. We can see that a sub 1 is 2, that r equals negative 1 third, and that n equals 5, so we can use the formula to get 122 over 81. Here's an exercise. What is the sum of the series 1 plus 2 plus 4 and so on up to 2 raised to k? So how many grains of wheat did the woman ask for? Could the king pay the woman? What if a series doesn't have a finite number of terms? What if it has an infinite number of terms? Look at a geometric series with a sub 1 equals 2 and r equals 1 half. If we add the first two terms, we get 3 halves. If we add the first 3, we get 7 fourths. First 4 terms, 15 over 8, and then 31 over 16. The sum of the first n terms approaches a set value 2. An infinite series is called convergent if the sums approach a fixed value like this. An infinite series is called divergent if the sums of the first n terms don't approach anything. When is a geometric series convergent? Consider an infinite geometric series, a sub 1 plus a sub 1 times r, and so on. Remember, the sum of the first n terms is a sub 1 times 1 minus r raised to n all over 1 minus r. Look at the 1 minus r raised to n in the numerator. 1 always stays the same. The second term, r raised to n, gets bigger and bigger if the absolute value of r is greater than 1. But if the absolute value of r is less than 1, r raised to n gets smaller and smaller. So if the absolute value of r is less than 1, r raised to n tends to 0. So the series is divergent if the absolute value of r is greater than 1, and convergent if the absolute value of r is less than 1. If the absolute value of r is less than 1, that means r raised to n tends to 0, so 1 minus r raised to n becomes 1. So in an infinite geometric series, the sum would be a sub 1 all over 1 minus r. Here's an exercise. Verify using the formula that the infinite geometric series 1 plus 1 half plus 1 fourth and so on is 2. There is a shorthand in summation. It uses the large symbol sigma, the letter s in Greek meaning sum. Let's look at an example. The expression on the bottom k equals 1 tells us that k is a dummy variable. That means it will be substituted for, but won't appear in the final expression. The bottom says that k will start at 1, and the top says that k will stop when it reaches 5. The dummy variables are incremented by 1s, and the values of what's in front of the sigma is added up for all different values of k. Let's have an example. The summation of k equals 1 to 4 of 2k plus 3. We have the terms 5, 7, 9, and 11, so the sum is 32. Let's have another example. Write this series in sigma notation. Since this is an arithmetic series, the n term is a sub 1 plus n minus 1 times d, or a sub n is 7 plus n minus 1 times 5. We use 102 as a sub n to solve for n, which is 20. So n starts from 1 and ends as 20, and our n term is 7 plus n minus 1 times 5, or 2 plus 5n, so the sigma notation would be this. Here's an exercise. Write the following in sigma notation. To write an infinite sum, the dummy variable would just go off to infinity. So we can write 1 plus 1 half plus 1 fourth and so on as this. Finally, let's talk about means. Consider terms in an arithmetic sequence, a sub n minus 1, a sub n, and a sub n plus 1, which are equal to a sub 1 plus n minus 2 times d, a sub 1 plus n minus 1 times d, and a sub 1 plus n times d. If we add the terms a sub n minus 1 and a sub n plus 1, we have 2a sub 1 plus 2 times n minus 1 times d, or 2 times a sub n. This means a sub n equals a sub n minus 1 plus a sub n plus 1 over 2. So in an arithmetic sequence, each term is the arithmetic mean of its neighbors. This can make us say, insert two arithmetic means between 1 and 4 to find some numbers x and y so that 1, x, y, 4 is an arithmetic sequence. Let's do that as an example. So a sub 1 is 1, but we don't know d. So we use a sub 4 to solve for d. Since a sub n equals a sub 1 plus n minus 1 times d, a sub 4 equals a sub 1 plus 3 times d, or 4 equals 1 plus 3d, so d equals 1. With d equals 1, we can find the arithmetic means 2 and 3. Here's an exercise. Insert 3 arithmetic means between 3 and 4. Let's have another example with geometric means, such as insert 2 geometric means between 2 and 16. So it's like we want to find x and y so that 2, x, y, 16 is a geometric sequence. We do something like the arithmetic series. Since a sub n equals a sub 1 times r raised to n minus 1, 16 equals 2 times r raised to 3, so r equals 2, giving us the geometric means 4 and 8. Here's another exercise. Insert 3 geometric means between 3 and 4. Finally, let's end this video with a short problem. As I was going to St. Yves, I met a man who had 7 wives, each wife of 7 sacks, each sack had 7 cats, each cat had 7 kits. Kits, cats, sacks, and wives, how many were there going to St. Yves? If you are trying to compute the geometric series 1 plus 7 plus 49 and so on, you are doing the wrong thing. Since the man, his wives, their sacks, and so on were met by the narrator on the way to St. Yves, they were leaving and not going to St. Yves. So the number going to St. Yves is therefore 1, the narrator. But of course, you could compute the sum of the geometric series as an exercise.